Hello, Assalamualaikum, and welcome to the second part of the video. So this is going to be the second part for rotational of rigid body. So in this particular video, we are going to continue our discussion on equilibrium of rigid body, and then we are going to continue with rotational dynamic, and then finally conservation of angular momentum. So the condition for a body or a rigid body to be in equilibrium, as we have looked in chapter 4, for a body to be in equilibrium, the net force or the sum of all the forces that is acting on the object has to be equals to 0. In chapter 8, we are looking at rigid body. So in rigid body, when you apply a force to the body, the force will have a turning effect on the body. So we have another condition for the body to be in equilibrium. So the second condition that the system needs to satisfy is that not only the force, this is the first condition. So the second condition is that the turning effect of the force has to add up to 0. So there are two conditions for a rigid body to be in equilibrium. The sum of the force is 0 and the sum of all the torque is 0. In the previous chapters, from chapter 2 to chapter 7, we are mostly dealing with a single point mass. So in chapter 8, we are dealing with a rigid body. So the mass is distributed throughout the shape of the body. So how do we draw the force of gravity on the body? So the way we do it is we use center of mass. So center of mass is a point, and we treat it as if all the masses is concentrated at that point. So in chapter 8, when you need to draw the force acting on the rigid body, you cannot represent it as a single point anymore. You have to draw the whole thing, and then you are going to choose a point, so at the center of the body, to represent the mass of the body. So the way the gravity acting on the object is we are going to draw the force of gravity on the center of mass. So this is the weight, that is the weight of the cylinder. The symbol that we use is WCM, stand for weight center of mass. So the same goes for the other shape, the spherical shape. So you have the spherical shape, weight of center of mass, and this is the beam. So we are going to use the center of mass to draw the force of gravity on the object. Alright, so in chapter 8, most of the problem that you are going to be dealing with, a beam or a bar. So the way you draw the center of mass of a bar is a point at the very center of the bar. So force of gravity on the bar is the W center of mass. So that is the force of gravity on the bar. So if, let's say, you have a problem where you have a ladder leaning against a wall, so the way you draw the force of gravity on the ladder is first you need to establish the center of the position or the location of the center of mass. So the center of mass is located at the center of the beam or the ladder. So the force of gravity on the ladder, we are going to draw it from the center of mass, and it's going straight downwards. So the same way as if we are drawing it on a single point mass, except for a rigid body or for the beam, we are drawing it on the center of mass. So we are going to label this weight as weight center of mass. So one of the application, as you look at here, we have a fireman lifting a person, so another fireman. So the fireman is applying the concept of center of mass. So a human being, if I can draw it for you, so a human being is very similar to a beam. So this is a human. This is the best drawing of a human I can do. So the center of mass of a human being is located at the center of the body. So the reason why the fireman lifting the person in this way is because because what he is doing is he lifting up the center of mass of that person. So that person here, so he lifting up the center of mass of that person. So here, so he's supporting the center of mass of that person on his shoulder. So by lifting the center of mass of that person, so you basically lift up the whole body. So this is the application of center of mass. So the most effective way to lift a person is using the what we call as fireman lift. Okay, now continue to torque. I believe that I've explained the idea of torque in the previous lecture, but for this one, what I'm going to emphasize on is on the direction of the torque. The equation of torque is torque equals to R cross F, which is also can be written as R, which is R is the distance from the turning axis, multiply with the force and then sine theta. Theta is the angle between the distance R and the force that we apply to the body. If the force that we apply to the body causes the body to turn in the anti-clockwise direction, we take the torque as positive torque or positive turning effect. So if the force that we apply to the body causes the body to rotate, so if the force that we apply to the body causes the body to rotate in a clockwise direction, we take the turning effect or the torque as negative torque. Now I'm going to show you a simulation to explain the sign convention that we use here. Okay, this is a FET simulation, PHET simulation. So basically we have a bar or a beam that is supported at the center of the beam. So if we draw the force on the beam, so we have the weight of the beam. So weight of the beam, the weight center of mass, and then the stand provide a reaction force to the weight. So the weight is supported by the stand, so we have a normal force. So at this instant, the sum of the force, because the beam is balanced, meaning that the sum of the force on the beam is 0, and because we have no other forces that is acting on the beam, so meaning that the torque on the beam is also equals to 0. Okay, now we are going to add a mass of 5 kg onto the beams. So if I have to remove my writing first. Okay, now if I bring the 5 kg and I put it on the 3 meter marks. So as you can see, the 5 kg turns the beam in the anti-clockwise direction. So what happened is the 5 kg, the force that we apply to the beam, caused the beam to rotate in the anti-clockwise direction. So the torque of the weight, so torque of the weight, the 5 kg weight, okay, we are going to take the torque as positive torque. Alright, because the force, the force by the 5 kg is turning the beam anti-clockwise. Okay, so I'm going to erase that and then move back the 5 kg here. What if we take the same mass and then put it on the other side of the beam? So if I place the mass there, so as you can see, the beam is rotated in the clockwise direction. So if I can draw the direction of the rotation, so the beam rotates that way. So this torque by the 5 kg, the same mass, is going to be a negative torque. Alright. Okay, what if we want the beam to be balanced? So if I remove it first, okay, put it back. So now it goes back to the equilibrium position. So we just support it on both sides and then we remove the support. So now the beam is balanced. So if we place 10 kg on the left, so let's say at the 4 meter marks, so the 10 kg, the force from the 10 kg will rotate the beam in the anti-clockwise direction. So we have positive torque there. So now if I place another 10 kilogram, but on this side of the beam, you can see that the second mass rotates the beam on the clockwise direction. So now the beam is balanced. So the 10 kilogram on the left try to rotate the beam in the anti-clockwise direction. So you have negative torque here. And then the 10 kilogram on the right rotates the beam in this direction. So you have positive torques here. And because they are at the same distance from the pivot, so this point is called a pivot point. Okay, it's called pivot point. So at the pivot point, the distance from the pivot point are the same. So the torque by the 10 kilogram on the right and the torque by the 10 kilogram on the left cancel each other out. That is why the beam is balanced. So let's say if I add a 5 kilogram, let me clear that out. So let's say if I add 5 kilogram to the right of the beam, so now the torque will not be balanced. As you can see, the beam is no longer balanced. So you have a net torque that is turning the beam in the clockwise direction. Okay, now we are going to go back to the slides. I hope you can see the sign convention that we use to determine the direction of the torque. So force that we apply cause the body to rotate in anti-clockwise, so the torque is positive. And if the force that we apply cause the body to rotate in clockwise direction, we take the torque of the force as negative. I'm going to provide one examples during our Google Meet session on how to solve a problem regarding equilibrium of rigid body. For now, we are going to continue with the next subtopic. So in the subtopics of rotational dynamic, in linear motion, we have force F. So when a force F is applied to a rigid body, it gives a turning effect to the body. So instead of force in rotational motion, we have torque, where torque is the magnitude of the R times with the magnitude of the force applied to the rigid body, and then sine the angle between R and F. And then for mass, in linear motion we have mass. For rotational dynamics, instead of mass as a measure of inertia, we have I. So I stands for moment of inertia. So moment of inertia, as we have discussed in the previous video, so moment of inertia is just an inertia for a rotating object. So it tells us how easy or how difficult it is to spin or to rotate a body. And then in linear motion, we have the net force equals to the mass of the object times the acceleration of the object. So if the force is unbalanced, the object will start to accelerate or decelerate. So in rotational dynamic, instead of force, we have net turning effect or net torque. So the net torque, because we are using moment of inertia for mass, and acceleration, we are going to use angular acceleration. So the equation for net torque can be written as I, which is a substitute for mass, and then substitute for the acceleration is going to be angular acceleration. The unbalanced torque that we provide to the rigid body will cause the body to spin faster or spin slower. So you are going to have angular acceleration. So to summarize the point that I've just made, so in linear motion, unbalanced force will result in the acceleration of the object. So either your object is going to be faster or slower. So in rotational motion, unbalanced torque or unbalanced turning effect by the force will cause the body to rotate either faster or it's going to be slower. Okay, I'm going to bring you to a simulation that illustrates the idea of unbalanced torque and angular acceleration. Okay, as you can see here, you have okay, this is a simulation from O physics. So this simulation is used to demonstrate the idea of rotational dynamic. Alright, so what you have here is a disk, and the turning axis of the disk is at the center. So we apply a constant force. So we have a constant force that is applied at the end of at the rim of the disc, and the radius of the disc is 2 meter. So from the center to the end, or to the circumference of the disc, is 2 meter, and the mass of the disc is 5 kilogram, and the force that we apply to the disc, because we apply the force at the end of the disc, so the torque, so as you can see here, this is the torque for 40 Newton meter. So the way we calculate the torque is we multiply the radius r, which is 2 meter, times with the force 20. So the torque that we apply to the system is 40 Newton meter. As you can see, there is no other forces that's balance the torque that we apply. So what will happen is that when I click the start button, you will see that the disc start to spin, and the spinning and the angular velocity will start to increase. So it starts slowly, and then eventually it will get faster and faster and faster. Alright, so as you can see, now the angular velocity of the disc is getting faster and faster. So the simulation has stopped. So with the torque of 40 Newton meter, the angular acceleration of the disc is 4 radian per second square, meaning that every second the angular velocity increased by 4 radian per second. Alright, so if we reduce the mass of the disc, what happened is going to, now the initial mass is 5. Now we have reduced the mass to 3 kilogram. So what you are going to see is that the moment of inertia of the disc is going to decrease. Then because of the rotational inertia has decreased, it is become easier to rotate the body. Then the result of that is that we are going to have bigger angular acceleration. So if I start the simulation, so we are still applying the same amount of torque, 40 Newton meter, but now the angular acceleration has increased to 6.67 radian per second square, because the moment of inertia of the disc is smaller. Okay, so I hope this gives you some ideas, or this helped you to understand the rotational dynamics of rigid body. We are going to go back to the slide. Okay, finally we are on the last subtopics in chapter 8, conservation of angular momentum. So I'm going to make a comparison again. So in linear motion, we have velocity v, the linear velocity v, and then mass m, momentum of p. So, and then the conservation law for linear motion is the sum of linear momentum initial is going to be equals to the sum of final momentum. In rotational motion, instead of velocity, we have angular velocity. Instead of mass, we have moment of inertia. So moment of inertia I. So instead of just momentum, we have angular momentum. The symbol for angular momentum is L, and angular momentum is also a vector. So in rotational motion, we have conservation of angular momentum, where the initial momentum of the system is going to be equals to the final momentum of the system. So because the equation for momentum is P equals to mv, so the equation for angular momentum is going to be equals to m will be replaced by I, and then the velocity is going to be replaced by omega. So that is how we calculate the angular momentum of a spinning body. But before we continue the discussion on conservation of angular momentum, I'm just going to do a quick revision on how to calculate the moment of inertia. So the equation to calculate the moment of inertia is given by the equation I equals to the mass times the r square. So r here is the distance from rotating axis. So in these examples, we have a mass that is rotating about this axis. So let's say the distance from the axis to the first mass is 1 meter, and then the axis to the second mass is also 1 meter. The first mass is 2 kilogram, the mass on the right, and then the mass on the left is also 2 kilogram, just to make things simple. So the way you calculate the moment of inertia of the system is that you add up the mass times r square, because we have two masses here. So the moment of inertia is going to be mr square for the first mass. So the mass is 2 times the distance is 1 square. You are going to add up with the second mass. So second mass is also 2 times with the distance square. So 2 plus 2. So the moment of inertia of this system is 4 kilogram meter square. So that is how you calculate the moment of inertia of a system of point mass. So these are the equations that you can use to calculate the moment of inertia for a disc, a hoop, a solid sphere, or a rod. So in the exam, so if you were given a rigid body, so you will be also given the equation to calculate the moment of inertia of the body, unless the question is asking you to find the value of the moment of inertia from the questions. Okay, now I'm going to bring you to another simulation where I'll show you how the moment of inertia is affecting the rotational speed or the angular velocity of rotating bodies. So this is a simulation from O physics. So what you have here is you have a disc that is rotating with an angular velocity omega, and then at the end of the disc you have a person standing at the end of the disc. So here it says that the mass of the person is 50 kilogram. So if I increase the mass of the person, if you can still remember the way we calculate the moment of inertia, so the mass times r square. So there are two variables or quantities that affecting the moment of inertia of a rotating body. First is the mass of the object, the second is the distance from the axis of rotation. Okay, now if we increase the mass of the person, alright, so we increase it slowly, so as you will see that the rotational speed start to decrease. It's becoming slower. Alright, so the rotational speed has decreased. So if you reduce the mass again back to its original value, around 50 kilogram, so you'll see that the spinning speed, the rotational speed or the angular velocity is increased again. So another quantity that is affecting the angular velocity is the distance from the rotational axis. So if we move the person closer to the rotational axis, so I've moved the person now closer to the rotational axis, you will see that rotation becomes faster. Alright, so you can calculate what is the new angular velocity of the disc and the person by using conservation of angular momentum. So if we move back the person back to the original position, to the end of the disc, you will see that the rotation becomes slower. So either we are increasing the mass of the person, or we bring the person closer to the rotational axis, so it will affect the rotational speed or the angular velocity of the spinning bodies. We are going to do some examples in the module mature regarding these topics. So for now, we are going to go back to the slide. So this is what I've shown you in the simulation. So originally you have a person with a mass of 50 kilogram, which is standing at the end of the disc, and then the person move closer to the axis of rotation. So this is the axis of rotation. So the disc is spinning with an angular velocity of omega. So let's say the distance here is 1 meter and the new 2 meter, and then the new distance here is 1 meter, and then given that the moment of inertia of the disc is 4, and given that the moment of inertia of the disc 400 kilogram meter square, and the angular velocity of the spinning disc when the person is standing at the end of the disc is 2 radian per second. Alright, so what is going to be the new angular velocity of the disc when the person move closer to the axis of rotation? So the way we are going to solve for that is we are going to use conservation of angular momentum. So conservation of angular momentum states that the sum of total angular momentum of the system initially is going to be always equals to the sum of the total angular momentum final. So at the beginning, so the person is standing at the end of the disc, so the mass of the person is 50 kilogram, and the radius from the axis and the distance from the axis of rotation is 2 meter. So the moment of inertia of the person is equals to 50 times 2 square equals to 100 kilogram meter square. So this is the initial moment of inertia of the person, and then moment of inertia of the disc. Then the moment of inertia of the disc is 400 kilogram meter square, and then the person, the same mass 50 kilogram, move closer to the rotational axis. Now the R is 1 kilogram. So the moment of inertia of the person has changed. So we have 50 times 1 square. So we have 50 kilogram meter square. But I of the disc is still the same, 400 kilogram meter per second. Alright, okay. So to find the new angular velocity of the disc, we are going to apply the conservation of angular momentum. So the total angular momentum, because both the person and the disc is rotating with the same angular velocity, so we have I1, I of the person, plus with I of the disc time with omega is going to be equals to after the person has moved closer to the rotational axis, they're still moving together. So I person plus I of the disc time with omega final. So this is omega initial. So we have 500 here. 500 times the initial angular velocity, which is 2, equals to 450 times omega final. So omega final is going to be equals to 1000 divided by 450 equals to 2.22 radian per second. So as you can see from the calculation, because the person moved closer to the axis, so the total moment of inertia of the system has decreased. So the angular velocity of the system has increased to 2.22 radian per second. The initial angular velocity of the spinning of the system is 2 radian per second. So that is how we apply conservation of angular momentum. I think that is it for this video. We are going to continue our discussion during the Google Meet session, and then we are going to do examples in the module modules. So I hope to see you there. Thank you very much. That's it.